Okay, let's go to the next section of what we'll be talking about today, which is integration by parts. So it's integration by parts is really cool because it's sort of like an extension to technique that you learn that only you guys know, and extension 1 and maths fast students don't know this technique. So it's kind of like a product rule for integration instead of like, you know how we had a product rule for differentiation? Well, this is sort of like a product rule for integration, but not really a product rule. It's sort of like a modified version. So we know that when we differentiate uv, we get u dash v's, or you can write it as v u dash plus uv dash. So basically what you can do is rearrange it so that you can get a new result, which is the integration by parts. So basically it's saying if you have an integral where you could express it as one of them is u, the other one is v dash, then you can, using a rearranged product rule, the integral of this is the same thing as u times v minus the integral of v u dash. So if you have an integration of two things, you just want to figure out which one is u and figure out which one is v dash. Then afterwards you can say that this is the same thing as uv minus the integral of v u dash. And this all comes from the product rule, and then we just rearrange it. You can see here I integrated both sides. I said uv is equal to that thing, and then I basically took this to the other side and then subtracted that. So basically it's on your reference sheet. This is what it looks like. So the thing is, as cool as this technique is, you should really try to save it as a last resort, because the thing, as I mentioned, it's kind of like the integration version of a product rule, but it's not really as easy and straightforward as just directly differentiating using the product rule. The problem with integration by parts is it's sort of troublesome compared to the normal product rule, because sometimes you might have to do it more than once. And you also need to be smart with which part of the integral you decide to be u and which part you decide to be v dash. Because as you can see, it doesn't directly integrate it for you. It just leads you to get another integral. You get uv, but you also get another integral. So there's a really cool mnemonic, a really cool rule of thumb that we extension 2 students are taught in terms of which one you decide to be u. So the mnemonic is liate. So this is a really useful mnemonic because it tells you the priority of which one you should let u. So it goes log, inverse trig, algebra, trig, exponential. That's what liate stands for. So if you have a log function somewhere in a logarithmic function in the integral, you want to prioritize giving that one to be u. So this is the priority list. Second is inverse trig. Third is algebra stuff, so constants or polynomials. Then it's trig, and lastly it's exponentials. So you kind of want to keep liate in mind when deciding which one is u. So let's say we wanted to integrate x squared cos x, like that. Well, the thing is, using liate, which one has priority to be u? Well, algebra is on top of trig. So x squared is algebra, cos is trig. Algebra has higher priority. So we're going to let u be x squared. And we're going to let v dash be equal to cos x. So therefore, when we differentiate u to get u dash, we get 2x. And when we integrate v, it will be the integral of cos is sine x. So remember that the product rule goes, when we are trying to integrate this thing, we will get uv minus u dash v. Like that. So therefore, the integral of x squared cos x dx is going to be uv, so it's going to be x squared sine x minus the integral of u dash v here, or you could say v u dash. So it's going to be the integral of 2x sine x. So you can see exactly that. Yeah, this is what we got over here. Now, the problem with this is you can see this thing here is still, we don't know how to integrate that yet. We've got a 2x times a sine x. So this is what I mean by integration by parts isn't as straightforward as the product rule. Like with the product rule, you could have just directly applied it and you would have gotten your derivative. The problem here is we just got another integral which we're not sure how to integrate. So let's just try doing it again. Let's try doing integration by parts again on this integral. So I'm going to let u be equal to, because lineate algebra gets priority over trig. So u be 2x, v dash, that's going to be sine. So u dash will be 2 and v is going to be negative cos. So therefore the integral is going to be x squared sine x minus, we've got uv, so it's going to be negative 2x cos x and minus the integral of negative 2 cos x, like that. So when I expand the brackets, I get plus 2x cos x. So this will be plus, but it will become minus 2 integral of cos x dx, like that. Okay, so now this is an integral we know how to solve, because we know the integral of cos is simply just going to be sine. So our final answer is going to be x squared sine x plus 2x cos x minus 2 sine x. And don't forget your plus c, because it's an indefinite integral. So tada, we just integrated x squared cos x using integration by parts. Note how we had to apply it twice in order to get the answer. So as the slides say, yeah, that's what your answer is going to be. It's going to be x squared sine x plus 2x cos x minus 2 sine x. And that's what we get when we integrate x squared cos x. Okay, we can now look at another example with integration by parts. And the cool thing about integration by parts is it allows us to find integrals of stuff we normally wouldn't have been able to find just by ourselves. Here, it's going to ask us to integrate inverse tan. So we don't know how to integrate inverse tan. Remember, we only know that integrating 1 plus x squared gives us inverse tan, but we actually don't know how to integrate inverse tan itself. So using integration by parts, we can do that. So remember lineate. The thing is, with integration by parts, you need to split it into two things, the product of two things. So here we only have an inverse tan, but remember, you can say that inverse tan is just going to be 1 times inverse tan. So there's still actually a thing being multiplied. It's just 1. You can say it, you can write it like that. So you can apply integration by parts. Now, which one are we going to let be u? Well, remember on lineate, inverse trig takes priority over algebra. So we're going to let inverse trig be u. So we're going to let inverse tan be u. So therefore, for v dash, that must be 1. So when we differentiate u, we get 1 over 1 plus x squared. And when we integrate v, we get x. So therefore, applying integration by parts, I'll get uv. So it will be x inverse tan x from 0 to 1, because those are our limits, minus the integral from 0 to 1 of u dash v. So this will be x over 1 plus x squared. Now, the thing here, I can plug this in. This will be 1 times inverse tan 1, which will be 1 times pi on 4 minus 0. And here, this is nice because in the denominator, we have 1 plus x squared. The derivative of that is going to be 2x. We want a 2x here, so I'm going to force myself to get a 2x in the top, but I don't want to change the question, so I'm going to divide by 2 in the front. So I'm balancing out the fact that I added a 2x. So this thing will now become pi on 4 minus half. Oh, this is from 0 to 1. This integral will be ln absolute value of 1 plus x squared from 0 to 1, like that. So therefore, this thing is going to be pi on 4 minus half ln 2 minus ln 1, which is going to be just pi on 4 minus half ln 2. So yeah, ta-da, we just learned how to integrate inverse tan. Here, it comes together nicely after you use integration by parts. Oops. So yeah, with to follow Lie, you just have a 1, then you would just let u be inverse tan and v dash be 1, and then you can apply integration by parts in order to get your result, which is going to give you pi on 4 minus half ln 2. So yeah, integration by parts is useful, but it can be cumbersome sometimes. But in this case, this was pretty straightforward. So yeah, it's really nice because it is basically a rearranged version of the product rule that helps us to do integration. Okay. So there are some special integrals where you have e to the power of ax sine bx and e to the power of ax cos bx. There's a special method to do these integrals that outlined in the A2 Notes Maths Extension 2 notes book. So if you're interested, you can go either purchase a copy from the bookstore, or you can get an unlimited subscription and you can read a digital copy for that. So as you can see, you usually use integration by parts when you're dealing with products of functions, but do you always want to use it? Remember, okay, so what the slide is trying to say is don't fall in the trap of always resorting to integration by parts as your default method. It's useful, yes, but you should try to use it as a last resort, because sometimes there are, as you saw from the earlier questions we did without using integration by parts, there are other ways of dealing with them. And sometimes you might miss an easier way because you always just resort to integration by parts. So, for example, if you had an integral like this, x e to the power of negative x squared over 2, would you want to use integration by parts? I mean, yes, this is the product of two functions, but notice how here, there's a function, the derivative of that function is actually going to be negative x. So what you could have done is here, just put a negative sign here, and then you get negative x. And then you can just directly integrate this entire thing, so you get negative e to the power of negative x squared over 2 plus c. And that would have been your final answer for this integral. Much easier using the reverse chain rule. So just be careful, make sure you read the question carefully when you're doing these sorts of questions.